Turkish aerospace industries just revealed something that challenges F-35 superiority. New prototypes with redesigned airframes and enhanced stealth features. Flight tests scheduled for spring 2026, as export deals worth billions already signed with Indonesia and potential agreements with Saudi Arabia. Turkey's KAAN stealth fighter program has progressed from concept to flight-ready prototypes faster than Western defense analysts anticipated. Turkish aerospace industries confirmed in January 2026 that the first true flight prototype will fly by May or June 2026. The program currently employs 3 dedicated flight prototypes with serial production deliveries targeted for 2029. The KAAN represents Turkey's first indigenously developed 5th-generation stealth fighter. The aircraft designation stands for Milli Muharip Uçak, translating to National Combat Aircraft. Development officially began in December 2010 when Turkey's Defense Industry Executive Committee approved the program to replace the Turkish Air Force's aging F-16 fleet, comprising approximately 240 aircraft. The first prototype, designated P0, completed its maiden flight on February 21, 2024. The aircraft remained airborne for 13 minutes, reaching an altitude of 8,000 feet and speeds of 230 knots. A second flight occurred on May 6, 2024, extending to 14 minutes at 10,000 feet altitude. These flights validated the aircraft's basic flight control systems and aerodynamic design. Turkish Aerospace Industries CEO Mehmet Demirolu revealed in January 2026 that the second prototype, designated P1, features substantial design modifications compared to P0. The revised prototype includes reshaped air intakes positioned further aft toward cockpit level. The fuselage rear geometry shows modified slope lines. These changes aim to optimize internal volume and improve stealth characteristics and accommodate sensor integration. The P1 prototype entered system integration phase in early 2026. Turkish aerospace officials stated that P1 and the third prototype, P2, are significantly more advanced than P0, featuring most mission systems planned for operational aircraft. Each prototype requires 2 to 3 months of ground testing before flight clearance. Testing includes system verification and resonance analysis, and fuel system validation and electrical testing. The program's timeline adjustment reflects typical development challenges for advanced fighter programs. Serial production deliveries moved from 2028 to 2029 to align with flight testing schedules and systems. Maturation and production readiness requirements. Turkish Aerospace plans to complete 3 additional prototypes designated P3 and P4 and P5 by 2026 for comprehensive testing campaigns. Physical specifications place the KAAN in the heavyweight fighter category. The aircraft measures approximately 21 meters in length with a wingspan of 14 meters and height of 6 meters. Maximum takeoff weight reaches approximately 27,000 kilograms. The design features twin engines and internal weapons bays, and stealth shaping incorporating radar-absorbent materials and angular surfaces minimizing radar cross-section. Propulsion planning follows a phased approach combining foreign and domestic engine solutions. Early Block 10 and Block 20 aircraft utilize General Electric F-110 GE-129 engines, delivering approximately 29,000 to 30,000 pounds of thrust each with afterburner. Turkey received 10 F-110 engines for prototype and early production use. Between 20 and 40 aircraft will employ F-110 engines before transitioning to the indigenous TF-35,000 turbofan. The TF-35,000 engine development represents a critical component of Turkey's strategic autonomy goals. TR Motor and TUSAH Engine Industries collaborate on the turbofan targeting approximately 35,000 pounds of thrust. Integration testing is scheduled for 2029-2030 with operational deployment targeted by 2032. This indigenous engine eliminates dependence on foreign suppliers and enables unrestricted export capabilities. Performance specifications indicate maximum speeds approaching Mach 1.8 with operational ceiling of 55,000 feet. The aircraft incorporates supercruise capability once equipped with TF-35,000 engines, allowing sustained supersonic flight without afterburner engagement. Combat radius exceeds 1,200 miles, providing operational reach throughout Turkey's strategic theater. The KAAN's stealth design employs multiple technologies reducing detectability. Radar-absorbent materials coat the airframe surfaces. Internal weapons bays eliminate external stores that generate radar returns. Canted vertical stabilizers and carefully shaped surfaces deflect radar waves away from emitting sources. The single-piece canopy design reduces radar reflectivity while providing superior pilot visibility. Avionics integration centers on the Murad 600A active electronically scanned array radar. This system surpasses capabilities of the Murid 100A currently employed on Turkish F-16s and Akunca unmanned aircraft. The radar supports simultaneous air-to-air and air-to-ground targeting, plus electronic warfare functions. Testing occurs aboard a Bombardier Global 6000 flying test bed, allowing engineers to collect performance data under realistic flight conditions. Sensor fusion capabilities integrate multiple information sources into comprehensive tactical displays. Distributed aperture systems provide 360-degree situational awareness, alerting pilots to threats from any direction. Electro-optical targeting systems supplement radar for passive target detection. Advanced electronic warfare suites protect against enemy radar and missile threats. Internal weapons bay configuration accommodates multiple munition types. The ventral bay carries long-range air-to-air missiles and precision-guided bombs. Side bays house short-range air-to-air missiles for close-range engagements. External hardpoints provide additional payload capacity for non-stealth missions when low observability becomes unnecessary. Total internal payload capacity reaches approximately 9,000 kilograms. Export developments demonstrate international confidence in the KAAN program. Indonesia signed a framework agreement valued at approximately $15 billion for 48 aircraft. Jakarta indicated preference for ITAR, free configurations powered by indigenous TF-35,000 engines, rather than early variants with American power plants. This agreement positions Indonesia as the first foreign customer. Saudi Arabia engages in advanced negotiations, potentially leading to formal agreements in 2026. Discussions cover procurement volumes ranging from 20 to potentially 100 aircraft. Proposals include possible local production lines aligning with Saudi Vision 2030 objectives, mandating 50% defense production domestically by 2030. Turkish aerospace executives stated in February 2026 that discussions are in final decision-making stages. Additional export interest comes from Pakistan and Azerbaijan and Egypt and the United Arab Emirates and Ukraine. Pakistan representatives finalized partnership plans in April 2025 for potential joint production. Egypt's participation includes co-production agreements announced in July 2025. These partnerships reflect strategic shifts toward practical industrial collaboration. The KAAN program addresses Turkey's removal from the F-35 program following Ankara's purchase of Russian S-400 air defense systems. This expulsion from America's premier fifth-generation fighter export program motivated Turkey's accelerated indigenous development efforts. The KAAN enables Turkey to maintain advanced combat capabilities independent of Western export restrictions. Operational doctrine envisions manned-unmanned teaming where KAAN fighters coordinate unmanned combat aerial vehicles. This concept, termed OKU system by Turkish Aerospace, enables collaborative missions with KAAN serving as command platforms directing autonomous systems performing high-risk operations. This approach mirrors American collaborative combat aircraft concepts for sixth-generation warfare. Turkish Aerospace's presentation materials indicate initial requirements for 148 KAAN aircraft, though clarification remains regarding whether this figure includes Indonesia's 48 aircraft order or represents solely Turkish Air Force needs. The first 20 aircraft enter service in 2029, beginning gradual replacement of Turkey's F-16 fleet slated for retirement starting in the early 2030s. Manufacturing infrastructure supports sustained production. Turkish Aerospace completed a dedicated KAAN assembly line, constructing major component assemblies vertically, including the 14-meter wingspan and 3.3 metric ton wing sections plus center fuselage. This vertical assembly approach optimizes workflow and quality control for composite-intensive airframe construction. Material science advances enable the KAAN's construction. Carbon fiber reinforced polymer composites provide optimal strength-to-weight ratios. These materials withstand extreme temperatures and structural loads while maintaining radar-absorbent properties. Advanced manufacturing techniques allow creation of complex, curved surfaces required for stealth shaping that would have been impractical using conventional materials and methods. The program stimulates Turkey's domestic defense ecosystem. Aselsan provides electronic warfare systems, and Havelsan supplies avionics and mission computers, and Roketsan develops weapons integration, and TEI contributes engine components. This industrial collaboration reduces foreign supplier dependence while building indigenous technological capabilities across multiple defense sectors. Turkey's achievement placing a domestically developed fifth-generation fighter into flight testing positions the nation among a select group. Only the United States and Russia and China previously fielded operational fifth-generation stealth fighters. South Korea's F-21 program and India's AMCA represent parallel efforts by regional powers pursuing aviation independence. The KAAN's rapid development timeline challenges assumptions about technological barriers to advanced fighter production. Turkey compressed development cycles that historically required decades for Western programs. This acceleration reflects focused investment in aerospace research and manufacturing infrastructure and engineering talent development over 2 decades.